grateful to Mrs. Prakash and the Prakash family for their munificent contribution to the Brahm Prakash Lecture Fund. A special issue of Resonance, edited by Professor Ranganathan and Dr. Baldev Raj, is being released shortly. Now to give you a brief introduction of the presiding Dr. Rodam Narasimha for this evening session. He is also a Padma Bhushan. Dr. Rodam Narasimha is presently a DSc Year of Science professor at the Jawaharlal Nehru Center for Advanced Scientific Research. He was educated at the University College of Engineering and at the Indian Institute of Science, Bangalore. He obtained his PhD at Caltech in 1961. He joined the IISc in 1962 and was associated with the Department of Aerospace Engineering in various capacities from that date till 1999. In 1982, he founded the Center for Atmospheric Sciences, now called as the Center for Atmospheric and Oceanic Sciences, which he headed till 1989. During 84 to 93, he was also the Director of National Aerospace Laboratories. During 89-90, he was Jawaharlal Nehru Professor of Engineering at the Cambridge University in England. He has also held various visiting positions in NASA Langley. He is a Fellow of the Royal Society and a Foreign Associate of both the US National Academy of Engineering and the US National Academy of Sciences. He has also been the Director of NIAS during 97-2004 here in the IISc premises. He has been closely associated with aerospace technology development in India at both technical as well as policy making levels. During 77-79, he was the Chief Project Coordinator at HAL and led the joint HAL-NAL IISc team carrying out the early conceptual studies for the LCA. As Director of NAL, he initiated and oversaw several major technology programs, including the development of carbon composite wings and flight control systems for the LCA. Under his leadership, NAL made the first parallel computer for the country in 1986 and fabricated and flew the first fiberglass aircraft in the country. He served on the board of directors of HAL for several years. He has also authored many books, and he has published roughly around 250 research publications in the fluid mechanics, aerospace science, and atmospheric dynamics. He has also co-authored and edited at least 15 other books, again in the same area of fluid dynamics and related subjects. So on behalf of IIM again, it gives us great honor to have Dr. Narasimha as well as Mr. Kiran Kumar here for this evening. Thank you very much. May I now request Dr. Rodam Narasimha to speak a few words about Mr. Kiran Kumar.
Dr. Kiran Kumar, Dr. Subramanian, my friends, office bearers and members of the Indian Institute of Metals. I first of all must thank the Institute of Metals for giving me this opportunity to do two things, both of which I treasure. One is that this lecture is in the name of Professor Brahm Prakash. He was here as Professor of Metallurgy and one of the very distinguished people on this campus when I came here as a student. I'm talking about 1953 now. And he was already a well-known figure, and his achievements have already been mentioned. Dr. Kiran Kumar is also an alumnus of this institute, and it's a matter of a great and particular personal pleasure that he is now chairman of the space program, chairman of ISRO and the Space Commission, and somebody who has slowly transformed himself from a career in physics to a career in technology management, especially in space. He was born in Hassan here in Karnataka, Old Mysore. Was a student here in Bangalore at National College, a place very well known to all people here. And then I think he got a BSc Honours in Physics from there, and I think that was the first time that they ran an honours course. Well, the honours course used to be common in Central College earlier, but for the first time that it was revived at the National College. And after that and after an MSc, he came to this Institute of Science to take an M.Tech degree in physical engineering. Now that takes me back to the days when that M.Tech program was started, and I remember in this very hall long discussions that went on whether that course should be started or not, because it was an unusual thing that the physics department was running a course in Master of Technology. So I am particularly happy and honored that we have here a person who is probably the most distinguished product of that course here. And I remember that Professor P.S. Narayanan, who really worked very hard to get that course going. I'm sure if he were around, he would have been very pleased to hear that he was in the second batch. Dr. Kiran Kumar was in the second batch, a second batch student, now heads the country's space program. Well, his special interests were in electronics, electro-optical imaging sensors and systems. And right from the time he joined ISRO, which was soon after he got the degree here, 1975, he has been involved in virtually all the projects or a whole range of satellites from then till very recently. And so that goes from Bhaskara and all the way to Mangalyaan, and maybe others which are still to fly. So he has led this program in ISRO with great distinction, and has made it possible for India's programs in many of these areas, in particular in remote sensing, image processing and so on, a major source of data for the country, and one major part of the space program. As all of you will know, the space program in this country started with the credo that it was really for the service of the people. And it's not, therefore, an accident. There's one of those things which is a household word in this country. So I think that Dr. Kiran Kumar has made extraordinary contributions in these areas to the space program. And on the Mars orbiter recently, which has been very much in the news, especially because it was cheaper there to make than a Hollywood movie, it's I think, kind of a very characteristic product of ISRO, and the orbiting maneuvers it had to go through in order to make it possible on a PSLV were one of the things where our speaker once again played a key role. He was director of SAC, Space Application Center in Ahmedabad, and from March 2012, and from January this year has been the chairman of ISRO. He's been widely honored for his work, Padma Shri by the President of India last year. He has won an award, Team Achievement Award from the International Academy of Astronautics, and an award for Cartosat in 2008, for Chandrayaan in 2013, so you can see that his contributions have been very steady and very widely recognized. He got the Remote Sensing Award from the Indian Society of Remote Sensing in 1994, and the Vaspik Award in 1998, the Astronautical Society of India Award in 2006, the Bhaskara Award in 2007, and so on. He is a fellow of the Indian National Academy of Engineering and the Indian Society of Remote Sensing, the Institution of Electronics and Telecommunication Engineers, the Indian Meteorological Society, and a member, corresponding member of the International Academy of Astronautics. And he has represented ISRO and India in many international bodies connected with space and with meteorology. So, it's a great pleasure to have you here, and I think it's particularly appropriate that an alumnus of the Institute is here to give a lecture in the name of one of the most distinguished academics that this Institute has had. And I'm honored to be able to welcome you here, Dr. Kiran Kumar. Thank you very much.
May I request Mr. Kiran Kumar to continue with the presentation, please? Thank you, sir. There's also a glass of water. Yes. Thank you.
Good afternoon to all of you, Dr. Narasimha, Dr. Subramaniam, and all the people who have gathered here. At the outset, I am extremely thankful to Indian Institute of Metals for inviting me to deliver this prestigious Professor Brahm Prakash Memorial Lecture on this 31st annual function. Many luminaries have delivered this annual Professor Brahm Prakash Lecture in the past. I am delighted and honored to be in such august company. Over 7 decades, Indian Institute of Metals has acquired a commendable position in the promotion of metallurgical engineering. I am thankful to the organizers for giving me this opportunity to deliver this memorial lecture and associate myself with this professional gathering. And I also would like to take this opportunity to excuse myself for being a little late, because it so happens that today we are completing 40 years of satellite instruction television experiment, and today morning in Ahmedabad we had a program commemorating this event, completion of 40 years of site. Site, as you may be aware, was one of the extremely important socio-technological experiment that was conducted by this Indian space program, wherein about 2,400 villages direct to community broadcasting was done by borrowing a satellite from America, and direct to community sets were set up, and broadcasting became a big event in the country. So you'll kindly excuse me for the delay, because I came directly from the airport to this place. Maybe you have already seen that Dr. Brahm Prakash was the first head of the metallurgy at IISc Bangalore, and he was the person who welded all the amorphous entities together at VSSC, a dynamic center as it is today. And his far-reaching decisions in design of 4th stage motor of SLV-3, which was also used as the apogee booster motor for Apple satellite. And he encouraged self-reliance and new initiatives like the miraging steel development. What I intend to do is just give you a glimpse of where we stand today in the Indian space program, and then get into how the space program has been trying to make use of indigenization in many important areas. See, today we have just completed about 122 missions, about 73 satellites, which encompass remote sensing, communication, navigation, and also the space science missions of Chandrayaan and Mars. We have launched about 47 launch vehicles, 4 SLV, 4 ASLV, PSLV 30, of which 29 are consecutively successful. Then we have the GSLV and launch vehicle for Mark III GSLV next version. And we have the space recovery capsule and the crew module. And in this period, we have also launched about 45 satellites for 19 different countries. Today, we have a fleet of about 29 satellites, 11 communication satellites, 4 navigation satellites, and about 13 remote sensing satellites, and the Mars orbiter mission. All of them are providing information in various ways and establishing the capability of this country in providing the use of space infrastructure for various activities. Recently, of course, you're also quite familiar that we completed the Mars orbiter mission. While the originally planned 6 months of operation is completed, the mission is continuing, and we just went through the phase of solar conjunction where for about more than a month we had no communication with the satellite. Subsequently, it has been established and all the payloads are operating, and the fuel left in the satellite is quite significant, and we expect this mission to last for a long time to come, particularly because the first conjunction period of 1 month where we did not have any communication with the satellite has survived, and it has gone through its internal autonomous mode, and because of this we have greater confidence, and the satellite does not have any failure so far since launch. And this also was among the top 25 inventions of 2014, and it won the Space Pioneer Award. Then in the Mark III, because last year we had the GSLV Mark III experimental care mission, where before the indigenous cryo engine for this was getting ready, we went ahead and then went through the phase of the first 2 stages operating and confirming the design adequacy of many of these stages. And in the process, we also made use of this launch for putting a crew module, which could act as a forerunner for future space manned missions. In the immediate future, we have a series of launches scheduled on 27th of this month. We have GSAT-6, which is carrying again a cryogenic engine, and it will carry the GSAT-6 satellite, GSLV Mark II, and then we have the AstroSat going up next month on September. Then we have a commercial launch for Helios. Then GSAT-15 we will be launching from Ariane. GSAT-15 satellite is a communication satellite. And we have the reusable launch vehicle technology demonstrator experiment. Then the 3 of the navigation satellites, which will complete our constellation of 7 satellites. Today we have 4 of these satellites in operation, and by March next year we expect to complete all these activities. Practically every month we have a launch coming up. Then the GSLV Mark II GSAT-6 mission, which is going to be launched on the 27th of August. Now the launch vehicle is at the launch pad and the various tests are in progress, and what you are seeing is the launch vehicle assembled. And this is also going to carry a communication satellite, which is GSAT-6, which is carrying a 6-meter diameter antenna, which is an unfurlable antenna, and this is one of the largest diameter antennas which we have built, and we are all eagerly waiting for the day it will be deployed in space. Sometime in the middle of next month, this event will happen, and this will provide a very significant communication capability to the country, because in the strategic sector this will be a very useful system. Then next month we have the AstroSat mission. It's a multi-wavelength astronomy mission, and again this is a very unique mission because this is for the first time globally anybody is flying on a single satellite many wavelength observation system, and we expect to launch this, and the satellite has already reached Sriharikota and the PSLV assembly is in progress, and next month around 28 we will be expecting to launch this. Of course, this we will also be having a reusable launch vehicle technology demonstrator. A scaled down model of a wing body is being put into space about 70 kilometers. Then it will come back through the atmosphere at about 5 Mach number, and this will give us some idea of the kind of issues that are involved and how well we have been able to appreciate the issues and build this system. Then the various activities that are going on is a semi-cryo engine. This semi-cryo engine activity is expected to be completed more or less in terms of the engine development by next year. And we are also working on air breathing technology and re-entry, and electric propulsion is another activity which we are doing. And we also have various the heavy lift launch vehicle development, and GSLV Mark III, for which the cryo engine development has been progressing very satisfactorily. We just recently completed 800-second test of a cryo engine, which is going to enable us to put about 4-ton satellites into geostationary orbit. And next year, December, is the target for launch of this. Now, in building all these launch vehicles, we have to make use of a large amount of materials, metals, and composites. And the kind of metals that we are using, whether it's magnesium, titanium, you will see in the subsequent slides, a very significant effort has been going on, and a large amount of indigenization of all this has happened. And almost about 80% of the launch vehicle is done indigenously, and materials itself, if you look at it, the cost of that is about 35% of the launch vehicle cost. Similarly, materials used in cryo engine and stages, you have a large number of different materials that are used: stainless steel, copper alloys, nickel alloys, titanium alloys. Then we are using also the aluminum alloys, and many of the items, including the filler wires, what are needed. And many of these are being done indigenously. And in the reusable launch vehicle, again, you have flexible external intrusions, then using the nose cap, which is a carbon-carbon silicon carbide coated, and the various materials that are used, composite materials that are required for this, including Inconel. Then similarly, in the cryo engine, semi-cryo engine, we have a large amount of development that is included, special coatings on to prevent metals, and then you have a large number of metallic and non-metallic material realization. And here again, almost about 40% of the materials are done within the country. And for the remaining materials, because of the quantity required is so small, that we have still not fully ventured into making them indigenously. Now, if you look at the service environment and the property requirements of some of these materials, when you are looking at liquid engines, now you have to reach up to 1400 degrees, and there is a corrosive propellant. Then you require high temperature strength, wear resistance, and corrosion resistance materials to be used. In the cryo engine, you have to go down to minus 253 degrees, low coefficient of thermal expansion, and low temperature strength and toughness materials. Similarly, in semi-cryo engines, you require to reach up to 900 degrees. And in satellites, we need to have large temperature excursion, and also it should be UV radiation, it should be able to sustain. Optical properties and thermal radiation are the issues that one need to worry about in the materials. Now, you require very high specific strength and specific module materials, then retention of mechanical properties down to 20 Kelvin, and easy fabricability, exceedingly high demand on performance reliability, and above all, we also need to worry about the cost effectiveness. And in the space program, we make use of steel, aluminum alloys, titanium alloys, magnesium and copper alloys, then some super alloys, composites, special minerals and coating, and also electronic materials. Coming to steels, merging steel is one of the developments that has happened, which we are all extremely proud of. Ultra high strength and having very high specific strength and high fracture toughness, and simple heat treatment and welding. The motor cases of all solid boosters are done using this material. And this particular program, which was started in 1982, has provided at Midani, we are able to produce both melting and forging of 800 mm billet, and then rolling forged slabs at Rourkela steel plant. Now, this picture shows some of the hardware that is getting realized in the plants, Rourkela steel plant. The first steel plate got cobbled during the rolling, and then the second slab successfully rolled to a plate, and this marked the beginning of maraging steel realization in the country. And the first maraging steel ring, 1.88 meter ring, was rolled at XJ Steel in Rajkot. And you are seeing the people who realized this standing in front of that. Then a certain amount of infrastructure built up for melting and processing, which happened at Midani, vacuum induction melting furnace, the vacuum arc remelting furnace, and also roller hearth furnace. They were all realized and have been extensively used for producing these materials, including the facilities like ultrasonic inspection facility and also the bogie type heat treatment furnace. And similarly for ring rolling at Bay 4, Chennai, these radial and eggshell ring rolling mills, then aging oven, vertical turning lathes, and all of these have been used for producing the items required for our launch vehicles. And you see in this picture of many of these facilities which are used for reheating or ring rolling process. Then similarly, some of the critical forgings that have been done, rings up to 5.5 meter diameter have been realized, and then N2O4 inlet flange is shown in this picture, and you also see some of the forgings that are part of the launch vehicle. Then among the steel, we also are using the high strength, low alloy steel, then the stainless steel 321, and then you are seeing in this the 4 mm thick rolled coils. Then this is all part of the C20 divergent segment. Then among the aluminum alloys, what we have the complete series from 1000 to 7000, and this slide shows you the different parts that are realized using aluminum, and a large number of them. And the process itself here starts from, you can see that from extruded billets, you are going into the billets, and then melting and casting activities, and the forging, then rolling activity, and also the sheets and plates. These are all done from aluminum alloys to the end product. And many companies are involved in this, like HAL, Bear Forge, Balco, Hindalco, then OFAL, OFAJ Nagpur. And here also a number of infrastructure have been established at these industry to produce these components. This is all at Balco Korba casting house. Then you have the infrastructure again continuing, and the material is cut to the length in the machines. Then you have the drop bottom solution treatment furnace. Then you have a plate stretcher, aging oven, then the packing machine, sawing machine. So all these facilities are established at the Balco for completion of the products. Then infrastructure for plates and forgings. You have the ring rolling and the drop bottom furnace at Bay Forge, the rolling mill and vacuum handling systems at Balco. Now this slide shows you, actually in 2002, we started with hardly 20% of these aluminum alloy based materials being indigenously done, and today we have reached around 86% of the material of aluminum is done indigenously. Coming to titanium alloys, again here you have the basic raw material at Midani, Hyderabad. Then you also have the closed die forging domes, and we are extremely happy to tell you here that recently the tanks we have been able, using these titanium tanks, they have withstood a proof pressure of burst pressure of 330 bar, whereas earlier we had reaching only about 280 to 290 bar. Now the whole process of using these indigenous titanium material, making these tanks withstanding almost up to 330 bar burst pressure has been realized, and it's been an extremely good development that has happened. Then you can also see that various titanium half alloy tubes at Messrs Nuclear Fuel Complex, Hyderabad. This is about 118 mm OD and 1.6 mm thick seamless tubes are made. Then similarly, the titanium sponge, this is done at KMML Kerala. Today the capacity is about 500 tons per annum. Of course, ISRO's requirement itself at the quantity that is required is less than this, but we are looking at ways by which KMML can now start probably exporting this and providing this material to other agencies also. Magnesium and copper alloys, we have this lightweight and high specific stiffness, and then electronic housings. For large amount of magnesium, we are using it for packaging electronics in all our equipment base, and then foundry practices are established. You have a largest casting outer axis gimbal as one of the main structural element for a 3-axis angular motion simulator realized using this. Similarly, for copper alloy, the vacuum furnace that was required, and also the copper plates for cryo engine. This also is a very important development, because what has been realized of this copper, the cost of procuring that was extremely large, and we are able to achieve a good product from this copper here. Then among the super alloys, if you see, we have a number of annealed and hot finished, cold and cold finished material which go into the nozzles, PS2 and GS2 engine parts, and also the columbium alloy which goes into the PS4 engine. This is used in both in sheet and rod form, and this is produced at Midani. Both of them are done at Midani. This is another super invar way which is used extensively in many of the electro-optical instruments that we build, telescopes, where we require attaching mirrors to the telescope housings using what we call mirror fixation devices. These also have been realized, the super invar, at VSSC with the help of Midani, and the critical technologies of melting, processing and heat treatment have been developed, and we are now building a 1.2 meter diameter telescope wherein these super invar materials are being used. Then a large amount of thermal protection and re-entry, both for SRE as well as CARE, where the silica tiles and also the medium density ablative tiles, and also for the current RLV-TD experiment, flexible insulation systems. These have been realized within the organization now, and the SRE experiment shows that the tiles survived satisfactorily the atmospheric exposure, and only there was some damage at the splashdown in the sea and handling, but otherwise the performance of these tiles have been extremely satisfactory. Then coming to some of the composite material used, for rocket nozzle, the nozzle throat inserts, then Kelvar epoxy motor cases, and also glass epoxy and dual graded reflectors, where these are used in as almost 2.2 meter to 2.4 meter diameter antennas on the satellites, and these all have been realized indigenously. Now again, some of the castings for cryogenic engine, if you look at the housing, this shows the kind of complexity that is involved in this particular component. About 12 types of highly critical and intricately shaped components are there in this. Investment casting technology for 11 types of the above are done along with HAL and Midani. Then this shows you some of the examples of the different types of pump casing that are used, turbine exhaust, then the second stage inlet, the body casting. And here many of the companies which are involved is Mrs. Omnicast, Kadalur, HAL, Koraput, IPCL, Bhavnagar. Then also Coimbatore, you have the Sunny's Alloys, and then the Gauri Ventures at Renigunta. Apart from this, we are also involved in making a large amount of magnetic material and electronic materials, and these magnets are used for AOCS thruster latch wall realization, and also the magnets for various applications in the both launch vehicle and satellite electronics hardware development, and also many shape memory alloys that are realized in the form of wires and plates. These are developed at VSSC and with some support from NAL on this. These materials are expected to be used for deployment mechanisms and also for unfurlable antennas. And some of the electronic materials that have been realized is for a 5 gigahertz oscillator material and a ceramic, then wideband dielectric filters, and also you can see the barium tantalate dielectric resonator materials. Then a large amount of, this is just a summary of some of those indigenization efforts that have happened, which shows from titanium sponge to copper cladded films. In this process, during the year, you can see where all these companies are located. Almost about 7 before 2000, almost about 12 after 2000. In all these places, ISRO has supported these industries to come out with the indigenous realization of these materials and components. And these materials have also been converted into the finished products, and this is a fairly wide distribution within the country. Then for the future, if you see, we are looking at for aluminum and lithium alloys, then aluminum beryllium alloys, and also aluminum carbon nanotube composites for cryo tank cages, satellite structures, and large space structures, cryo and interstages. Then we are also looking at about 50% more specific strength than the AA2219. Then lithium, and also the lithium ion cells and batteries which are being fabricated today both at VSSC and ISAC makes use of materials. Of course, raw materials are all coming from outside. So there is an effort now to bring in the technology indigenously for producing these materials within the country. And probably some of you would have read yesterday Gadkari making a statement that government has tasked ISRO to develop these lithium ion batteries for transport sector. So there is a significant amount of work involved in this. Then similarly, in terms of aluminum oxide, then zirconium and carbon-carbon composites, a host of material both for near-term and medium-term developmental activities are being planned for thermostructural materials. Then similarly, thermal protection systems, both in terms of silica tiles, metallic material and metallic tips, in the carbon foam and foam-based material in thermal insulation. And there are many challenges in realizing this. And we are looking at between 2015 to 2030, if you see that a host of materials and technology complexity, which is going from nanofluid for heat pipes, and then for microthrusters. Then you also have nanostructural materials to reduce the weight of both the launch vehicle parts as well as the satellite parts. The new horizons and the frontier areas, if you are looking at high strength, low density alloys, then you have aluminum, lithium, and aluminum beryllium. Then you have large structures, cryo tank cages and satellite structure, thermostructural materials, metal matrix composites, intermetallic composites, for air breathing engine, satellite microthrusters, then RLV wing leading edge, then similarly carbon-carbon composites. Then you have the advanced thermal protection systems, which are required for both RLV as well as laser gyro and mirror blanks. Then nanomaterials for structures and tank cages. So we have a long way ahead for making sure that we are able to provide various materials and metals required for our future requirements. And elements processed together form an alloy with an enhanced property symbolizes the teamwork which is the hallmark of ISRO, and ISRO has been able to produce many of the systems primarily because of the extensive teamwork that happens, and we have also been able to enthuse many of the companies within the country. And currently the situation is the ecosystem within the country is growing in such a way that both in terms of investment, new investments, and the government support for making these Make in India and things happen is improving. And now there are many companies which are coming forward to invest on their own and produce the new requirements. So we have a wonderful opportunity to do a lot of R&D activities and indigenize these materials. Not only indigenize these materials, but probably we should also be looking at producing new kinds of materials which have not been done so far, and we could become leaders in future instead of being only the followers where what we have been doing so far. I think with this I'll close my presentation. Thank you very much.
There are a few questions to the speaker. If the like to answer them. Yes.
Subsystems and so on. And so many of them were from smaller places like Renigunta and Kadalur and so on. Is there a conscious strategy on the part of ISRO in terms of vendor development? Because these obviously are much smaller players than SAIL and Hindalco and other such big companies. So if you can shed some light on what that conscious strategy has been, that would be wonderful. Thank you.
No, I think what you are saying is a very important point. See, while we have worked with the large companies also like HAL or even Godrej or Midani or many of them, but when it comes to making certain parts from this, it has been definitely our endeavor to see how we can make use of people at even remote places. Of course, in some of the cases, it is purely the initiative on the part of certain companies to come forward and work with us. That is one of the key things, of course, in any effort, unless the other side is also willing to do the thing and take certain risks in doing, it doesn't happen. But what we have been trying to see is find out people who are prepared to take some initial risk, because the kind of work that happens here is volumes are not large, requirements are small, and companies are not likely to make any profit in the process. So, but there are large number of people who, for the sake of doing something new, something for ISRO or for something for the country, they are prepared to work. So these are the type of people who have taken up, and they have worked for not just few years, almost decades. So there is a certain amount of the interest in those parties to work with, because they are not working for really profit in this. But probably things could change now, because now we are getting into a phase where from few launches in or one launch for few years, now we are getting into 10 launches per year, almost 15 launches per year, and we are getting into a phase where the PSLV production, we are trying to get it done through the industry. We are looking at a mechanism where the entire PSLV will be integrated and launched at Sriharikota by a consortium of industries. We have set up a mechanism now, it's going through the study phase, interacting with the industries, and probably the things could change, not only because of this, but also because globally what is happening is the rate at which things are happening have increased. Today we have, very recently we had interaction with few of the companies. They are looking at building 600 satellites and launching them in 4 years. That means almost each launch will take about 20 satellites, and so there is a large demand which is growing, and they are also looking at Indian companies, and they are ready to tie up with Indian companies because the Indian companies now have the experience and also the talent that is there. So they are trying to, now we are supporting this activity both in electronics and material fabrication. So this situation is going to be quite conducive for industry to take up and move forward.
Have we started work on stealth technology, means radio wave absorbing material, microwave absorbing materials?
No, we are not doing anything on
For DRDO will be.
that. Right.
Follow up on the very last point that you made, which is related to it's amazing the extent of indigenization which has gone compared to 2000 up to whatever it is right now. But we are still dealing with traditional materials. The new materials haven't seen. I see that you're still projecting aluminum, lithium alloys as future materials. There have been future materials for 50 years now. My question is there a strategy in place at ISRO for development of new materials? Because it is a time-consuming process, whereas you're on a mission mode and you operate at a different timeline. Is there a strategy, technology readiness levels, or let's say ICME, integrated computational materials engineering type approaches which are coming into play to expedite this process of new alloy deployment into applications?
Yeah, you have a very important point. But what you need to appreciate is, see, just now we are reaching a phase where for one of the launch vehicles, we are coming into a full production phase. So obviously, when you get into from an experimental developmental to an operational phase, you are not likely to get into the kind of activity what you have said. But at the same time, now we are looking at, for example, for future launch vehicles or heavy lift launch vehicles or different things. Obviously, if we go with what is traditional, maybe it's not sufficient. Now it is in this place, I think we really need to address this, and probably in the next couple of years, we are going to look at giving more emphasis on development of newer materials which will go into the future systems, rather than just replacing what we are doing. Currently, as you are aware, what I told also is we are looking at just replacement or what is not available from outside, making it happen here. But I think for that we need the support of academic institutions and research institutions to come up with new materials which can be used. And currently, while we are looking at GSLV Mark III and GSLV Mark II and PSLV operationalization, now the future system that we are looking at, in that how to make use of different materials, we'll have to worry about that. And I'm sure in the next couple of years we will be trying to. One of the things we are currently trying to do is, earlier we had what's called the RESPOND program, where we used to support academic institutions and R&D of 2 to 3 years time period, costing maybe about 20 to 30 lakhs type of funding. But now we are looking at a mechanism where we want to get into a different phase, where about 3 to 4 years time frame and maybe a couple of crores type of thing. But the activity will be open for anybody. We will inform, okay, this is the kind of requirement we have. Now, whoever comes up with a good proposal will be given a large fund, and then within a short period, they will produce that. Okay, we'll have to take risks. Some will succeed, some will not succeed. But we are getting into this process. We have the initial approvals taken. We are going to announce such mechanisms maybe before the middle of next year. It should get into operation. So we are looking at relatively larger funding on specific developments It could be components, it could be systems, or it could be materials. Yes, sir. Okay, now coming to your the first point, of course, large amount of development, whatever has happened. Now, how to make this accessible or available for development in the country, whether it is going to be a production. Probably the conditions are becoming more and more conducive for such a thing now is what I would feel, both because the way the government is approaching, as well as our own organization also, we are reaching a stage where we can probably now look at the developments and then make it available to the industry. We have started in some ways where we have started showing up in our website. If you see any of the center website, we have an industry portal. For example, Ahmedabad, if you look at Space Application Center, we have started an industry portal a couple of years back. And then we are trying to showcase what all is available for the industry to use in various areas. So this is going to get a push, and then each of the centers will come up with more and more, and we will try to do on that. Now coming to your second point on the Uttarakhand, there are two parts to that. One is, if you look at the in terms of identifying a possible event that had happened, we had at Ahmedabad sort of alert of heavy rain events. Now the heavy rain event was actually about almost 18 hours earlier it was pointed out. But what you have to appreciate is, today for cyclones, for example, we have a fully working model where NDRF, National Disaster Relief Mechanism, I am coming to that. So there is a fully established mechanism where, given an alert, there is a system which gets into action, puts it in place, evacuates people, and does. Now, for example, if you talk about Uttarakhand disaster, we do not have today a system which is giving an early warning system, and that early warning system is accurate and credible enough for people to start putting systems in place and then do the necessary corrective measures. We still have some way to go before you can say all such weather events can be predicted or brought in with greater. Of course, our part is only in terms of providing the necessary inputs from space-based observation and some ground-based observation. We are not actually in the process of doing the predictions, etc. That is still mainly part of IMD. But we are conducting some R&D, and we are also running some high-resolution weather models. And using this today, if you see MOSDAC, there is a website which shows for the entire country if the rain is likely to be more than certain predetermined threshold. It is going to happen in next 6 hours, 12 hours. We have started doing this on an R&D basis, but still there is a certain distance to travel before the kind of solution what we have for cyclones available for other events. Thank you, sir. I think this is one of the very important aspects which we debated a couple of months back in what we are calling it as threat See, today, in terms of space technology and space agencies, are actually facing a threat from space commerce and industry. Yeah. See, many of the space agency heads, we have had a couple of meetings with them. They are feeling that the governments are no longer going to support them for the kind of for the kind of money they are demanding for performing and providing the kind of services that the space agencies are providing. This is because today in the space commerce is growing in a very big fashion. Now, like whether it is an aircraft industry or shipping industry, from starting, if you see, you are having space tourism, then you are having people who want to go into space for a couple of days of travel and come back, space adventure, then even space exploitation of mining on the asteroids, etc. And there are many private companies which are now, for example, America is now doing the cruise, ferrying the cruise to the space station is done by private companies. So once the private company starts operating, the way in which things happen, that pace at which it happens is very fast, very quickly it changes. Like I mentioned to you that we are having today a OneWeb company which is planning to produce 650 satellites at the cost of something like 450,000 per satellite and 150 kg satellite each. So they are trying to make it happen in a matter of 4 years and put all of them into orbit. Following that, it will become 900. But the point what I am trying to say here is that industry is coming in a big way, because now they are seeing that there is a market, there is money they can make in this, and they are going to make a sea change in the way work is happening. So agencies like ours, if we are complacent, we may become obsolete also. It's not very unlikely that it is quite possible. There will be some areas, of course, strategic areas where the governments may still decide, yes, this is the only way it can happen. But the kind of thing that is happening is really a point where we need to introspect and change the way we are working to remain both relevant and also bring in. So what we are looking at in ISRO, for example, is we want to enable in the country more and more people to take such opportunities which are available globally, tie up with other industries, they become part of those manufacturing and then providing things. So we are starting, at least we have been able to now tie up with few of the companies which are now doing business directly with the international companies. So they will produce items which are used both in satellites and launch vehicles, both for Indian use as well as for the international use. So one of the things is we need to enable more and more within the country people. So that is what is the task ahead of us.
Hello. You mentioned the reusable launch vehicle is still in the development stage. So when will it start launching satellites? And one more question is that will we have a human spaceflight program? And if yes, then when will that happen?
Reusable launch vehicles, we are just at the beginning, very first step. See, what we are doing is a technology demonstrator, a scaled down version of the wing body being put into orbit, and at Mach 5 it will come back. So we have a series of experiments before we even finalize the configuration of that launch vehicle itself. So that is where that stands. Coming to the human space program, still we have the requirement of the government finally approving that India should start doing a human space program and going ahead. Currently what we are doing is we are trying to do certain key critical technology development activities like crew module and then pad abort tests, certain developments of certain materials and tiles, etc. So those activities we are doing, but unless the government finally says, yes, India is ready for taking up a space program and give the funding, it is not going to happen in the immediate future.
Dr. Kiran Kumar, for not only having given this lecture here, but also answered all these questions, because it's been a very busy day and has come from Ahmedabad just this evening in order to be able to give this lecture. So I think it was a wonderful occasion, one where, in the memory of Professor Brahm Prakash, spaceman as well as an academic here earlier. Present chairman of ISRO has talked about the materials programs of the organization and about the future that they see for it. So on behalf of all of you and on my own behalf, I want to thank you for this lecture and for the great trouble that you've taken to fit it into your program. Thank you very much.
May I request Ms. Pushpa, the secretary of the chapter, to... Sorry. I'm sorry. Pushpa.
Yes.
Thank you.
Hello. On behalf of IAM Bangalore chapter, I like to thank Shri A.S. Kiran Kumar for delivering a 31st Brahm Prakash Memorial Lecture on my favorite indigenous development of materials for space program. I'd like to thank Professor Rodam Narasimha for presiding over the lecture. I'd like to thank Materials Engineering Department of Indian Institute of Science for all the support given for organizing this lecture. And special thanks to Public Relations Department for providing this facility, good facility. Importantly, I'd like to thank IAM members, students, and staff of IASC for being with us. It's been great pleasure. Thank you. And I request all of you to join for high tea organized just across the room, this hall.